Hi all, this is Vasu Sham, and this is Theoretically Podcasting. In today's episode, I'm going to go over my PhD defense. I defended my PhD in July of 2020, if I'm getting that right, during the pandemic, and therefore it was a remote defense. And I had to prepare a 20-minute presentation, which was to be followed by a Q&A session with the committee. And I had recorded a mock version of my presentation beforehand. And what I'm going to go and do today is use that video, but do a live voiceover just to highlight my current thinking about the various ideas that I had done my PhD on, and later to highlight some of the related and follow-up work that came out of it. Now, a lot of this work that came after isn't necessarily mine because there were a number of related ideas that I was trying to address within my PhD. And it's very gratifying to see how far some of these ideas have been taken by my colleagues, fellow researchers, in the 2 years that have passed, and what the potential is for these ideas in the future. So here is my PhD. So the title of my PhD thesis was the Quantum Gravity Renormalization Group. This was a play on Sung-Sik Lee's idea of the quantum renormalization group, the gravitational aspects of which I was focusing on. And so, with the suggestion of my supervisor, Lee Smolins, I decided to take this as the title of the thesis. It's a little bit aspirational. Didn't quite get to construct what I would have really liked to call the quantum gravity renormalization group, but maybe I discovered a clue or two at best. So there were roughly three parts that this thesis was broken into. The first part dealt with the basic question of how to take the scale radius duality of ADS-CFT seriously when we have to contend with the fact that in the bulk, local diffeomorphism invariance means we ought not to treat any direction as privileged, whereas it's hard to see how the energy scale from the perspective of the quantum field theory is not privileged. Now, in typical ADS-CFT settings, this isn't much of an issue because we're dealing with an asymptotic boundary and we have conformal invariance there. And we can just see that the changes in energy scales or in local length scales are just symmetry of the theory. Where it does become an issue is in the setting that I focus on in this thesis, which is where the boundary has been brought to a finite distance from any bulk observer. In this setting, we really have to grapple with the fact that theories that exhibit local gravitational bulk duals are peculiar in that they respond to local changes of scale, either energy or length scales, in such a way as to treat the energy scale or length scale on equal footing with the other directions in the field theory, thereby manifesting the local Lorentz invariance in the bulk. Now, this convoluted sentence can be succinctly encoded in an integrability condition of the local renormalization group flow of the boundary theory. And that is what I wrote down first in 2016 and called the holographic West-Zumino consistency condition. Now, it turns out that the flows, or theories that satisfy these peculiar conditions, have peculiar locality properties of their own. In particular, it seems that the UV properties of the entanglement entropy are quite different than in local quantum field theories that we're used to, namely that calculations of entanglement entropy seem to yield finite results as we take the length scales to be small. And there are also behaviors that are somewhat reminiscent of the gradient flow smearings that are studied in lattice QCD sometimes. And finally, as we all hope, understanding the holographic dictionary better should tell us something about quantum gravity in the bulk. And here, the idea is understanding these peculiar quantum field theories that have a peculiar kind of integrability condition that they satisfy. It should tell us something about quantum gravity in regions of finite spacetime volume. This thesis was based on the following papers, and I would like to thank my collaborators, Paul Zaputa, Shruvik Datta, William Donnelly, Andre Pereira, Elise Lepage, Yang Li, Edward Mazank, and Ronak Soni. Now, the first question one can ask when we state the scale radius duality is how it comes to be that the radial components of the bulk equations of motion, or the radial constraint equations, can possibly map to RG equations. Setting aside the specific form of these constraint equations, just the fact that they are local equations in space leaves us with the question of how to think about RG flow equations, which we normally see as ODEs for the coupling constants under a change of a fixed energy scale, can be related to local gravitational field equations. And Sung-Sik Lee partially answered this question when he said that we really should think about the renormalization group the way Osborne, Shor, and others taught us to, which is to first turn all the sources, first turn all the couplings into local sources, including the source for the energy momentum tensor, that is the metric. So put the theory on an arbitrary background of both geometry and various other couplings, and then ask how the theory responds under an infinitesimal Weyl transformation. The response equation under these infinitesimal Weyl transformations is a local generalization of the Kalan-Simansky equations. And these local Kalan-Simansky equations have the structure that maybe can be related to some kind of constraint equations for some special class of theories. And that idea was developed quite a bit by Sung-Sik Lee. And my own work was to try and interrogate how the local Lorentz invariance or diffeomorphism invariance in the bulk is encoded in the local renormalization group flow when we make this identification. So to be precise, in the bulk, what we're interested in are the components of Einstein's equations that generate normal and tangential deformations of a hypersurface embedded into spacetime. The context of interest here is to take that hypersurface to be the fixed radius locus on which we expect the dual theory to live, which is a hypersurface of what we would think of as constant radius instead of constant time, which is how Arnavut-Dieser and Missner originally conceived of the constraint equations. And the constraint equations in our case are just the same as those of the original ADM, except that there are some differences in the signs appearing in the radial scalar constraint equation. So the scalar constraint equation generates the normal deformations of a fixed radius hypersurface, and the diffeomorphism constraints, the vector diffeomorphism constraints, generate the tangential deformations, and their weighted sum is the total Hamiltonian of the theory. So the Hamiltonian of a diffeomorphism invariant theory is composed purely of constraints. The only place where these can have or these can generate true evolution is when these hypersurfaces have some corners, and that's how it comes to be that when we have an asymptotic boundary, we can have a true Hamiltonian, but that's localized purely on the asymptotic boundary. Now, focusing just on the constraints for a moment, we should note that they have a Poisson algebra on the phase space of general relativity. So it's on the phase space of the metric spanned by the metric and its conjugate momentum. These constraints have a Poisson algebra, which is so constraining, pun intended, as to fix the functional form of the scalar and vector constraints themselves. So the statement is that having fixed the phase space to be that of the metric and its conjugate momentum, the Poisson bracket algebra of the constraints is powerful enough to fix the functional form of the constraints themselves up to the sign of the cosmological constant and the sign of the relative term between the kinetic and potential terms in the scalar constraint. This uniqueness condition was first pointed out by Hochmann, Kukash, and Titelbaum and can be seen as the Hamiltonian version of Lovelock's theorem. And note that the tangential deformations satisfy a diffeomorphism algebra of, well, tangential to the hypersurfaces, basically. So the Poisson bracket between two constraints with different Lagrange multipliers is just the vector constraint with the Lie bracket as the Lagrange multiplier. Whereas the more rich structure comes when we take the Poisson bracket between two scalar constraints, that is two normal deformations, with different Lagrange multipliers sigma and sigma prime. And their difference is actually a tangential diffeomorphism with a very particular structure of the Lagrange multiplier, or the shift, fixed in terms of sigma and sigma prime. So it is this structure that fixes the form of H of sigma. Now, given these properties and given a version of the bulk boundary correspondence, if we are to identify the local radial constraint equation with the local Kalan-Simansky equation as per the prescription of Osborne and Shor, then the Poisson algebra maps to the large n limit of the so-called Wess-Zumino consistency condition. So the left-hand side, that is the Poisson bracket between two scalar constraints with different Lagrange multipliers, maps to the commutator of two generators of local RG transformations with different Weil parameters, acting on the generating function. And my observation was that for the consistency of this identification, we just need to identify what the right-hand side means. And the right-hand side is basically the tangential diffeomorphism constraint smeared with a very particular combination of the lapses. With the identification of the lapses with the local Weil parameters, all that we need to do is smear it against the boundary manifestation of the diffeomorphism constraint, which is nothing but the condition that the energy momentum tensor is covariantly conserved. So in other words, the local Kalan-Simansky equation is subject to the holographic Wess-Zumino consistency condition, which is to say that indeed Weil transformations commute, but they commute on account of having the energy momentum tensor be covariantly conserved. And this, through a transliteration of the uniqueness story in the bulk case, translates to the fact that delta sigma of Z is fixed entirely, provided we're focusing only on the metric as the source in G. So if we restrict our attention to having only the metric be dynamical, so this is a very peculiar small class of quantum field theories. It's unclear to what extent they exist, but say they exist, then well, the only deformation that preserves the local bulk diffeomorphism invariance or local bulk Lorentz invariance is the one that is given by the following, which is a Weil transformation compensated by the deformation of the theory by a certain quadratic combination of stress tensors and the addition of the bulk Ricci or the boundary Ricci scalar. So this is one of the main results, which is to identify the T-squared deformation, which is the name for this particular combination of stress tensors, which in 2 dimensions becomes a TT bar deformation, with the unique answer to the question of who can satisfy the Wess-Zumino consistency condition. And so this is just a slide highlighting what I just mentioned. And of course, when we go down to 2 dimensions, it becomes the TT bar deformation. Note that deformations involving other operators other double trace operators can capture bulk matter. And I might have more to say about that later. Now, one of the first things that I wanted to understand was what kinds of properties these deformed theories in general can satisfy. First was that when we do these deformations, there's a sense in which the generating functions satisfy, or the sources satisfy so-called gradient flow conditions. And what do I mean by that? So let's take a step aside from the whole holographic story I've been building so far and just consider the nonlinear sigma model. And there, this is just an example, but there what the gradient flow equations would be are the following. We extend the dynamical field, which I call sigma superscript A here, to not just depend on space, but also on this parameter lambda. And the extension into the lambda direction is dictated by certain covariant gradient flow equations. And the object with respect to which we take the gradient is just the NLSM action itself, where we replace the field sigma with the field sigma of lambda. And then what we find is that to leading order in the coupling lambda, the solution to this flow equation looks like a heat kernel smearing of the fundamental field sigma. So movement along this additional direction leads to certain delocalization from the perspective of the original theory. And this has been put to great effect in various problems pertaining to lattice QCD. And in the context of the irrelevant operator deformations that appear in finite radius holography, what I argued is that the resulting RG flow equations for the sources, such as the metric and say the source of some scalar field, are nothing but some version of the gradient flow equations that I mentioned before. Now, the difference is that we're not actually dealing with the action of the theory itself that lives on the boundary, but rather the induced action that is obtained by integrating out all the fundamental fields of the boundary theory so as to obtain some non-local functional, putatively, that depends only on the sources. But now these are some non-local gravitational theories involving only the boundary metric and other boundary fields. So this is the story where, unlike S induced, the object, the functional S here, actually is just local in terms of the float fields G and phi. And Jackson et al. In this very nice paper in 2013 dubbed these the geometric RG flow equations. So in much the same way as local field operators under the gradient flow are smeared, it seems that these deformations induce a certain smearing of the fields of the induced gravity theory obtained by integrating out the fundamental fields. So there's this sort of Legendre transformed picture in which we have a gradient flow. The next thing that we wanted to do was investigate the properties of entanglement entropy in some of the simplest of these deformed theories. And not only is this maybe a simpler setting than the more general setting I was talking about before, but it also happens to be one of the most famous examples of these deformations, that is the TT bar deformation. So with my collaborator, Will Donnelly, we looked at the simplest possible case where we can compute the entanglement entropy through the replica trick in a TT bar deformed large C CFT. And what we found was that the resulting entanglement entropy is ultraviolet finite. The setting we chose was to study the Hartle-Hawking state prepared on the hemispherical slice, basically on the boundary of some hemisphere of the TT bar deformed CFT on a two-sphere. And what we did was we cut this equatorial circle that bounds the hemisphere into two. And so our entanglement entropy was computed for half of the equatorial circle. And this configuration has a spherical symmetry, which we exploited to great effect to use the flow equation and the conservation law for the stress tensor to solve for the stress tensor components. And then we use the relation between the stress tensor and the generating function to obtain the entanglement entropy. As I said, I will comment on follow-ups to all the ideas that I present here, and there have been some very interesting follow-ups to this work. But the bottom line was that unlike the CFT counterpart of this calculation that led to a logarithmic divergence at small radius, the TT bar deformed entropy, entanglement entropy, remained finite as we took the radius to be small. As we took the radius to be large, it agreed with the CFT result. And this is a sense in which the TT bar deformation provides a UV regulator for the holographic CFT that we started with. And that intuition is consistent with the fact that there's a scale radius duality, and having brought the boundary inwards in ADS3 CFT2, we now have that the UV divergences of the CFT as we originally had them that were mapped to the IR divergences of the bulk ADS space have been regulated, given that our bulk space is now bound by a finite Dirichlet wall and is therefore finite volume and can therefore not have any IR divergences that arise from there being infinite volume. And we managed to show that if we use the identification between bulk and boundary variables as dictated by Megov, Meze, and Verlinde in their pioneering 2016 paper, that we recover a finite radius version of the Ryutakeyanagi prescription. Namely, the minimal surface that in this case is a geodesic that is anchored to the entangling surface, that in this case are the two antipodal points, has an area, which in this case is a length, that equals the entanglement entropy when we compute it from the boundary perspective. We also showed that Dong's generalization of the Ryutakeyanagi prescription to the so-called conical entropies that are close relatives of the Renyi entropies, that he argued are dual to the area of a cosmic brane in an orbifolded version of the bulk ADS space also agree when we compute them on either side of the dictionary. So to learn more about this, do see Will Donnelly's and my paper on entanglement entropy and the TT bar deformation. Funnily enough, given how we set up the calculation, we were able to access the n goes to 0 limit of these conical entropies, which actually computes the rank of the reduced density matrix. And it looked as though that too was finite and resembling in form of the rank of a reduced density matrix of a theory defined on a finite lattice. This property actually is a manifestation of a more general, interesting operator algebraic feature of coupling bulk quantum fields to gravity, which is that a type 3 von Neumann algebra goes and becomes a type 2 von Neumann algebra. But that too shall be commented on in the follow-up section of this podcast. So more on that later. But I should say that this kind of feature is also key in using these deformations to study bulk de Sitter physics. Now, finally, what I wanted to understand was whether these deformations can tell us anything about bulk quantum gravity, at least in 2+1 dimensions, where it seems that there's an understanding of what quantum gravity should mean, because the theory is essentially topological. But how are we to go about this? And the idea was to say that, well, the large C partition function very clearly maps to the Hamilton-Jacobi functional. The large C TT bar flow equation is a change of variables of the Hamiltonian constraint equation. And now we make the leap. We gauge fix and quantize the Hamiltonian constraint when we pick the topology of the constant radius sphere here to be that of the sphere, and obtain a quantum theory with a one-dimensional Hilbert space involving only the S2 wave function. Now, what is the analog of that move on the field theory side? I'm not entirely sure. It's some choice of scheme, which fixes how the holographic Wess-Zumino consistency conditions are satisfied. But the idea is that if we just read off from the result of the gauge-fixed radial constraint equation what the S2 partition function of the TT bar deformed theory should satisfy, then, well, we have an equation for the S2 partition function of the TT bar deformed theory. And so the game would be to start here in the bulk and then figure out what happens when we go back to the boundary. And what's nice about the analysis in the bulk is that when we fix a certain gauge, then the problem reduces to a finite dimensional phase space whose quantization leads to quantum mechanics on a finite dimensional Hilbert space. Or rather, that's not quite true. It's really a Hilbert space of a quantum mechanical system. That's a better way to put it. So the magic gauge fixing is the constant mean curvature gauge. And the idea is to first isolate the trace of the momentum conjugate to the metric, and then impose that the trace of the extrinsic curvature, which then becomes the trace of the conjugate momentum divided by the square root of the determinant of the metric, is spatially constant. By spatially here, I mean along the constant radius surface. This is called the constant mean curvature condition. That then gives us a separation between the trace and the trace-free parts of the momentum tensor. And then the momentum constraints tell us that the trace-free part should give us a transverse and trace-free tensor sigma mu nu. On the sphere, such tensors identically vanish, and so there is a major simplification where all we have to deal with is the constant mean curvature object tau and its conjugate, which is just a cousin of the radius. Now, the Hamiltonian constraint under this decomposition becomes the so-called Lishnerowitz equation. And on S2, what we find is that there's a unique zero-mode solution to this equation. And instead of using the zero-mode solution to eliminate this constraint, we instead take the constraint and evaluate it on the zero mode and treat that as a residual global constraint equation. So we're going from a local constraint to a global constraint. And then the quantization of this global constraint basically gives us a Schrodinger-like problem, which then lets us obtain the sphere wave function. And then we use the mapping between the partition function and the radial wave function to obtain the sphere partition function of the TT bar deformed finite C conformal field theory. And we studied solutions to these constraint equations and chose certain boundary conditions to fix the integration constants and obtained a solution in terms of a confluent hypergeometric function. Now, an alternate route to obtain this is the so-called kernel, which was studied by Laurent Friedel, Migo et al., and Andrew Tolley, and also me and my collaborators Ronak Soni and Edward Mazank. This provides a way to define the TT bar deformed partition function purely in terms of its seed counterpart and a functional integral kernel involving frame fields E and F. The idea is that if Z0 satisfies the conformal anomaly equation, then Z of F satisfies the Wheeler-DeWitt equation with a certain choice for the coefficient of the Ricci scalar term. And what we looked at was the radial reduction of this simple equation. And in that radial reduction, we found that the very same constraint equation is satisfied, but here the integration constants are fixed for us by the kernel. And here's the solution where the integration constants have been fixed beforehand. And also the bonus here is that the large R or CFT limit has been baked into the construction. And here's a summary of the various bits and papers that were involved in this thesis defense. So I happened to pass this defense after a fairly interesting round of questions and answers, and then obtained my PhD and moved on to my current position at Stanford as a postdoc. But there have been quite a few interesting follow-ups to the works that I described and the ideas that I described in this defense. That's what I'll talk about next. So stay tuned. Hi, so now I want to go over some of the references of some interesting follow-up works to some of what I did during my PhD. And this list is by no means exhaustive. It'll certainly touch on some topics that I hope to return to with some of the authors in future episodes. In particular, the very first one here, which is about what's called Cauchy slice holography, where the idea of equating the partition function of a deformed holographic conformal field theory to solutions of the radial Wheeler-DeWitt equation in ADS has been upgraded to identifying solutions of the quote-unquote actual Wheeler-DeWitt equation on Cauchy slices is identified with a certain kind of deformation of the holographic CFT uh, beyond a certain range of parameters that had been entertained in the radial case. So to get a better sense for what was happening in that paper, we will have the authors join us in a future episode to talk more and explain where their idea came from. So this work, inspiring as it is, definitely upgraded some of these older notions in the whole literature about Dirichlet wall holography to then take this wall to literally become the Cauchy slice. And it thereby realizes this fact that in some sense, the most interesting aspect of holography isn't so much the reduction to a codimension 1 surface starting from the bulk of the dynamics, but really more of a codimension 2 reduction, which is in some sense the reduction to data on the boundary of a Cauchy slice itself. In any well-posed initial value problem, it is just the initial data specified on a codimension 1 surface that determines the future evolution of a system. We don't consider this to be holographic, of course. So what's special is that there's a further reduction to one lower dimension. And that idea touches on other related work involving holography in flat space and how if you push this Cauchy surface out to the two null surfaces forming past and future infinity, past and future null infinity, then the statement is that all of the data on these null surfaces can be recovered from the data very close to the past boundary of future null infinity or vice versa. And then there's set of works going back to the point about gradient flows and their relation to holography. There is the group in Kyoto with the Shinya Aoki, Shuichi Yokoyama, and their collaborators Yannis Balog and Tetsuya Onogi, who have very interesting constructions involving the direct application of some of these gradient flow ideas to some scalar models and other conformal field theories. And they have an interpretation of the information metric being the bulk metric and seeing the emergence of a certain kind of bulk geometry from the gradient flow itself. So this is the generalized gradient flow as it is conceived in the lattice QCD literature. So that set of ideas has been explored over here. And when it comes to the calculation of entanglement entropies, I really must point out this follow-up paper by Lukowitz, Liu, Silverstein, and Toroba, where they extended the calculations that my collaborator Will Donnelly and I did first to arbitrary subregions, well, regions of arbitrary shapes, including intervals and such, and also to the model of de Sitter holography that Silverstein, Toroba, and Gorobenko put forward, where in addition to the TT bar deformation, there's a deformation by the boundary cosmological constant, the so-called lambda 2 operator, which then takes us from a finite Dirichlet wall in the bulk of ADS space to a finite Dirichlet wall, very similar locus in de Sitter space. And there are different patches of de Sitter space, the de Sitter space that this wall could bound, including the static patch itself. Now, in all three of these, I suppose, subcategories, there have been many other works that have extended some of the ideas that I discussed in many other ways. But I just wanted to highlight the ones that I felt like I have a good appreciation for from having closely read them. I would be happy to discuss more papers, provided you tell me what I should read in the comments. So this was a shorter than normal episode of theoretically podcasting, but I do hope to be accompanied by guests in future episodes, and that will lead to more longer and more interesting discussions where I get to learn more new things as opposed to just highlight some of the work that I did over the course of my PhD. But I hope this is of some value to somebody. Thank you all for listening, and tune in next time.